So next what I want to do is I want to describe parabolas in a way that you haven't seen before, possibly. Okay, maybe you've seen it, maybe you haven't, but there's a nice geometric property that parabolas have. And so the idea with a parabola is that you're given a line called a directrix, and you're given a point, which I'm going to call F, which is the focus. And then the parabola is going to be the set of all the points that are going to be the same distance between the focus and the directrix. So for example, this point right here, it looks like it's about the same distance from the focus as the directrix. And something like, just eyeballing it, but maybe something like that point would also be on the parabola, because if you were to compute the distance from the focus to that point, and then the distance from this point down to the directrix, okay, so here we'll go straight down. Those look to be about the same distance, okay? And so the parabola is going to be the set of points that are that same distance from the focus to the directrix. Okay, and so this has just a very nice geometric interpretation of what exactly a parabola is. And so it turns out that if you look at y equals x squared over 4p, so if that's your parabola, this is a parabola. So this is a parabola with focus. It turns out the focus is 0p, and directrix y equals minus p. Okay, and so that's what that parabola is, and that's basically how you can deal with all parabolas. If you have parabolas that open sideways, so rather than up and down, so if you were to have a parabola that would open something like over here, I'm still just going to assume for now. So this just reminds me that for now, what I'm going to deal with is the unshifted conics. So things like circles centered at the origin. I guess we dealt with circles in general, so I'm not going to say anything more there, but ellipses centered at the origin. Here, parabolas where the vertex, the bottom point or top point of the parabola is at the origin. And then we'll talk about shifted conics later. So what happens when you take this curve and then you shift it all over the plane. Okay, we'll talk about how to deal with those, but first we'll deal with unshifted. So really there's only two cases for parabolas. Either they open up or down or left or right. Okay, and so if they open up or down, they're going to be basically what we had before, except with a plus or minus in front. And if they open left or right, then you just switch the role of x and y. And so this is going to be the parabola x equals y squared over 4p. And that's going to have focus p0. So basically you just switch the role of x and y. And then again, switch the role of x and y. So this looks like the directrix is going to be x equals negative p. Okay, and then if you change p to be a negative value, so I've drawn both of these graphs with positive p values, but if you were to take p and make it negative, so for example, if you were to look at, say, y equals x squared over negative, I don't know, let's just make it negative 8. This would be x squared over 4 times negative 2. And so our p value is going to be negative 2, and therefore our focus is going to be 0p, and the directrix is going to be y equals minus p. Okay, and so you end up with this graph. So you end up with x squared over negative 8. It's going to have focus 0, negative 2, and then the directrix is that line y equals 2. And then this will open down. Okay, and so really that's everything that I can think of that I want to say about parabolas. So with parabolas, we have the focus, we have the directrix, and then once we know that, we know basically everything else. Okay, so I think that's everything I wanted to say there. And then the last conic that I want to deal with are hyperbolas. Okay, and so hyperbolas are going to turn out to have a formula such as x squared over a squared minus y squared over b squared equals 1. And so this is a hyperbola. And what I want to do is I want to think about what this graph is going to look like. And there's a few things that I want to do here. So first, let's just kind of generally graph this. Okay, we'll talk about all sorts of different properties with these hyperbolas. First, if x is equal, excuse me, y is equal to 0. So if this term is gone, in other words, then we see that we have solutions when x is a or minus a. And we call these points the vertices. So the vertices are going to be a 0 and minus a 0. Let me just say plus or minus a 0. And notice that if x is equal to 0, well, there's no solutions there because you would have negative y squared over b squared is 1. Negative y squared over b squared is less than or equal to 0. And in particular, it can never be 1. So there's no value where the curve is going to cross the y-axis, where x is 0. And so, of course, that's true of any value in between here. But what ends up happening is that you end up getting a curve that's going to look something like this. So it's going to look something like, just keep in mind I can't draw. So we'll look at some pretty pictures maybe, probably in class. Okay, but we'll talk about some hyperbolas here. And so hyperbolas are going to open up like that. Okay, so that's generally what a hyperbola is going to look like. And then there's a few other properties here. So there's the focus. And the way that we interpret the focus here is a little bit less intuitive than the way that you interpret the focus with parabolas or ellipses or circles. But the idea here with the hyperbola is that you still have a directrix. Okay, and well, actually, this will be a little bit easier to talk about in the next section. But you still have a directrix, and the hyperbolas are the set of points where if you compute the distance between the focus and let's actually get rid of the directrix, because I think that that might actually obscure things for now. Okay, and like I said, this will be a little bit easier to explain in 10.6 when we're still going to talk about conics, so we'll see what that's all about soon. But the focus is going to be the set of points where, the focal points are here, and the hyperbola is the set of points where if you were to compute the distance from one focus to the next, okay, and then if you were to take the difference of those distances, it's the difference of those distances that is constant. Okay, and then forget about the directrix. We'll talk about that much later. Okay, but the focus is going to be these points such that the points on the hyperbola are the ones where the difference of these distances. So, for example, if we were to call this L1 and L2, this L2 is a terrible line. But if you were to look at L2 minus L1, that's going to be some value. And then if you were to look at this point up here, let me actually draw this with some points here. So this is a little easier to talk about. So if you take this distance and that distance and call this L2 and L1, and then you were to look at L2 minus L1, you get some certain constant. And it turns out that that's actually the defining property of the hyperbola. And you can do this with any point. So pick another point on the graph, say over here, and then compute the distance between the one focus and the other. When you subtract them, let's call these values L3 and L4. If you were to look at L4 minus L3, that's going to be the same constant. Okay, so it's like 5 or 7 or so, whatever that constant is. That also has an interpretation related to the directrix, which is why I brought that up before, but we'll talk about that later. So hyperbolas are these sets of points. It's kind of the locus, the collection of all the points where the difference of distances between the focal points is constant. Okay, so that's a hyperbola. And with a hyperbola, we have a few other properties to talk about. So of course we have the vertices, which are kind of the innermost points, or when the hyperbola is centered about the origin, I think of the vertices as the points closest to the origin. Of course, when we talk about shifted conics, that interpretation will change, but that's what the vertices are. And the focal points are going to be on the same axis as the vertices. So here the vertices are on the x-axis. And so that means that the focal points are also going to be on the x-axis. And it turns out that these are given by plus or minus c comma 0, where c squared is a squared plus b squared. Okay, so that's what turns out to be the focal points for a hyperbola. And then the last thing to talk about is that there's one other kind of property that these hyperbolas have. And this is kind of hard to interpret via my graph, but we'll do the best I can. It turns out that when you look at the long-term behavior of hyperbolas, so if you were to look at these graphs, it turns out that these almost get linear. Okay, so these hyperbolas almost become linear, and they get kind of straighter and straighter and straighter as lines. So it turns out what's going to happen is that there's going to be asymptotic lines that kind of hug the curve when x is large in the positive direction and large in the negative direction. So in other words, when x is close to plus or minus infinity. And so you get these asymptotes that are going to look something like, that was pretty terrible, but not too bad. So let's try it one more time. You get something like that. So that would be one asymptote. And then by symmetry, you get another. So it would look something like that. Okay. And so you get these asymptotes. These asymptotes should go through, let me just fix that. These should go through the origin. Okay. And so these asymptotes, these purple lines, there's a few ways that you can kind of define them, but the way that I like to do this is because I always forget the formula. So I always have to sit down and I take 30 seconds to figure it out. We're looking at the curve x squared over a squared minus y squared over b squared. And so what I want to do is I want to look at the quantity y over x as x goes to infinity. And so let's do this. There's a few different ways that we can do it. Let's clear denominators. Okay, so we're going to get b squared x squared minus a squared y squared equals a squared b squared. So it's fine. Let's divide both sides by x squared. So we're going to end up with b squared minus a squared y over x squared equals a squared b squared over x squared. And one other thing we can do is we can divide both sides by b squared. So we're going to end up with a over b squared, y over x squared, and this is going to be a squared over x squared. And so something is bothering me here in my calculation. Something is bothering me here. Yeah, what I want to do is, yeah, this calculation is wrong, so I apologize. I'm bad at video editing, so that's what it is. So let's look at the line y equals mx. So we know it goes through the origin. So we just have to figure out what's the slopes of these lines. And what we can do is we can take that and plug that into our equation, x squared over a squared minus y squared over b squared. And if we do that, we end up with x squared over a squared minus mx squared over b squared. equals 1. And so what's going to happen once we do the algebra is it's going to turn out that we're going to get m is b over a. And actually, because of the square, you get plus or minus b over a. And so our asymptotes are y equals plus or minus b over a x. Okay, and that's what this graph is going to look like. Okay, and so really we have kind of 3 defining properties with hyperbolas. We have the vertices, we have the focal points, and we have the asymptotes. And then we can do the usual thing if we switch the role of x and y. Okay, so if we look at, instead of x squared minus y squared, if you look at y squared minus x squared. Then what's going to happen is you're going to have a hyperbola that's going to open up and down. So it's going to look like that. Again, terrible drawing, but you get the idea. And the vertices, so we're just going to switch the role of x and y. The vertices are again going to be when y is equal to a or minus a and x is 0. So you get 0 plus or minus a. The focal points are again going to be on the major, or they're going to be on the same axis as the vertices. So we're going to get 0 plus or minus c, again, where c squared is a squared plus b squared. And then the asymptotes are going to be y equals plus or minus a over b x. So what I did is I actually switched the role of x and y here. And so if you switch the role of x and y, you get x equals plus or minus b over a y, or y is equal to plus or minus a over b x. Okay, and so those are the asymptotes. Okay, and so that's more or less everything that I wanted to say about hyperbolas. Once we actually go through and talk about some of these examples in class where I have numbers a and b, I might rederive that formula for the asymptotes, because I wasn't very happy with how I did that here. And so rather than doing this in general for all values a and b, I might just do this for a concrete term. Okay, but that's generally how we handle conics. So we have circles and ellipses. We have parabolas and hyperbolas. Okay, so those are the kind of 4 conic sections that we're going to deal with. So in the next video, we'll talk about shifted conic sections, and we'll see exactly how we can handle all those.